Yeah, so I think, did everybody hear that? How do we control the pressure? The idea is that with the supply fans on a variable speed drive, we'll control to a pressure in the room that's slightly positive. And with the exhaust fans, we'll control to a pressure that's slightly negative, either in the plenum or actually putting some sensors in some of the chimneys here. So the fine tuning of it will need to happen. It will require that when you got this rack assembly and there's no rack there, that there's a blank off panel. So it's not going to require absolute, perfect containment, but it is going to require best practice as far as, okay, we want to have, we don't want a lot of air bypassing, because what that will do is it will cut into this exhaust temperature. Instead of 95, we'll end up with 85. But again, it won't be a disaster. It will mean we just have less capacity available.
Yeah, just looking for the dampers on the return to control the pressure for how much gets sucked up each
Yeah.
side. If you short circuit your entire room, it won't happen with the row.
Yeah. So you mean dampers on the exhaust here? Yeah, there are going to be manual balancing dampers on those as well. Yeah. So if you have an area that has no racks in it at all, instead of having to put a bunch of blanket panels, you just shut off that exhaust. Yeah.
Two questions. How do you handle non-conforming equipment that's not rack mountable, such as I heard we have IBM and Sun here?
Yeah.
P-Not 595, we have Sun 9000 projects, Sun 9900 Victor. Cisco's been a big fan of putting side discharge in for devices.
Yeah.
Much of that. And my second question is, what occurs on a utility outage? And what's your temperature transit during utility outage?
Yeah. So the first question, we did design for a certain amount of equipment that dumps its heat right into the air, and tape machines and things like that. This data center wouldn't be good if you came in and said, I don't want to put anything in the rack and I want 200 watts per square foot. We're not going to do this hot aisle, cold aisle containment. But you know what? Any data center at 250 watts per square foot is going to have a huge problem if you don't do containment of one form or another. It's a problem. So anyway, it does depend on a large percentage being contained. I think in our CFD, it was somewhere around 10 or 15%, we said, are not contained and are just dumping their heat into the room. Bad boys, like Cisco, right? So, and what was the second question again? Sorry.
Utility outage?
Yeah.
And peak temperature transit?
Yeah, so the whole idea with the utility outage is that this, all the control system will be on UPS. We might end up with some pumps on UPS, but the chillers will have to restart. The fans will restart once the generators kick in, which will be in about half a minute. So, or less, 15 seconds or something. Bob, where's Bob? Yeah, so once the generator...
Plant, so don't confuse it with our UPS plant, but yeah, it's a typical startup time for any generator.
Yeah, so about 15 seconds. Now, so there will be a little bit of a heat rise during that time if the fans are off, right? But the numbers that people talk about are in the minutes. So we're talking about in the seconds the fans get back going. And the beauty of it is when you have airside economizer in this climate, which is almost all the year, it's able to do cooling. If the chillers take a little bit longer to start up, which they usually do take a minute or two instead of seconds, the fans will be pumping and will be doing the airside economizer. So, next. Okay, we just talked about that. And what we're looking at is this fan array system. One of the main suppliers that people are familiar with is the Hunt Air fan wall. But actually, it doesn't need to be Hunt Air. They don't actually have a patent on making a wall of fans. They have some other patents. So it could be the Hunt Air. We're thinking that Hunt Air would be the right one because they have a direct drive fan, which is belts, no belts and less failures. And then they also have this box with sound absorbing material in it, so you don't need to put in extra silencers, which costs extra energy and fan energy, pressure drop, and therefore money. So we're setting them up with 8 fans. I think it's 10 fans per VFD. For every 10,000 square foot module, 8 fans and 4 VFDs can fail altogether, and we still have enough air. So we've got a lot of redundancy built into the fan capacity. And again, here's that thing where the economizer does provide additional redundancy. We are going to, at all times, even in full build out, have an extra 750-ton chiller is redundant.
Is that 75% constitute the combined of 100% of partial or 100%?
That would be, the 75% of the year, we're at full economizer. If you say with partial, it's more like 95% of the year, 98, something like that. So when we talk about energy efficiency, we did basically what boils down to 4 major moves. One was the flywheel UPS, which does save a good amount of energy. This air side economizer, we have very efficient fan system, and then the efficient chilled water plant. It's not that complicated. So when we put it all together, we did an hourly analysis on the whole system, not just a spot check, but a deep hourly analysis, the same type of analysis that PG&E requires for their rebates, and came up with a PUE of 1.12. Now, you know, it's an estimate, and that compares to 1.4, 1.46, 1.5 for a typical new data center with a chilled water plant that doesn't do air side economizing. That's where we would be. And you know, the LBL benchmarking, the average data center is about 1.8. Those of you familiar with the LBL stuff. So there's a lot of legacy facilities out there, especially the ones with air-cooled cracks that have pretty poor PUEs. This is just a graph from the LBL work on UPS efficiencies. And you can see that the flywheel, the flywheel UPS, the guys in red up here are the most efficient ones. So there is a big efficiency benefit to using those guys. On the fans, how we got them to be efficient, we did a variety of things. We first selected very efficient fans, right? A lot of engineers just ignore the fan efficiency. And if you ignore it, you'll end up with a fan that's 50 or 60% efficient. We looked at it, and these fans, the way we're setting it up, are going to be 73, 74% efficient. We're doing this low face velocity, that is low air speeds across the filters and the coils, so low pressure drop. And we're ending up with this total static pressure drop of 1.05 inches. And a typical, if you look at just to give you a sense, a crack unit or a craw unit, those guys are typically operating at 2 to 2.5 inches of static. So that directly relates to fan horsepower. And then we are using, counting on a relatively high temperature difference, 25 degrees. And the higher the temperature difference, the less air you need to move. So if you look at the watts per CFM, this is a great metric to use to look at your fan system when you're doing a design or looking at an existing facility. How many watts do I have to use for every CFM of air that I move, cubic foot per minute? And if you look at a crack unit, it's about 0.4 watts per CFM. An air handler, more of a standard piece of equipment, 0.3, and we're at right around 0.24 watts per CFM. Yeah.
Does the air handler include the chiller and other mechanicals behind it?
In this watts per CFM?
Yeah.
No, it's
It's
just
just
the
a fan.
fan watts for every CFM. Yeah, this is not like a kilowatts per ton type of number. Yeah. Okay. The other thing is the chiller system. It will be used for about 1,500 hours per year, plus or minus. So we are designing it to be efficient. And the interesting thing is that this is this kilowatt per ton, the efficiency. And lower is better, less kilowatts for every ton. We wanted to push the kilowatts per ton down. And this is the tonnage, the load. And what happens when you design for a warmer chilled water temperature, we're doing around 55 degrees. The efficiency improves significantly compared to a 42 or 45 degree chiller. Okay, so this is 42, 45, that's the standard temperature that we design to as mechanical engineers. But when you're doing a 70 degree supply air temperature, we don't need 45 degree chilled water. 55 is fine.